Hi, and welcome to Dr. V's Chemistry webcast. In this webcast, we're talking about the contributions of a few key scientists and how they helped the first atomic theory to be discussed. And we're going to focus on just those key people and leave an awful lot out. This is a very focused presentation on the scientists who are likely to show up on a first-year high school chemistry test, and it is by no means comprehensive. So I wanted to start by talking about some ancient Greek philosophers, because they spent a lot of time debating the nature of matter. It was all about argumentation. It was all about ideas. What they didn't do was experiment. And that's okay. That wasn't their way of operating. But I do want to mention a couple of prominent people. One very prominent ancient Greek philosopher was Aristotle. And Aristotle was one of the leading voices in the idea that matter is infinitely divisible. You can cut it up into smaller and smaller and smaller pieces, but they still are matter. And he also said there were four main elements: earth, air, fire, and water. And these ideas persisted for a long time. Aristotle's views were really, really dominant well into the Middle Ages in Europe. And that's okay. But I really want to focus on Democritus. For the purposes of my high school chemistry classes, Democritus is the name that you need to know. He is credited with being the first person to argue that matter is made out of small particles. We don't really know that much about Democritus. He's sometimes referred to as the laughing philosopher. We don't know that much about his life or the details of his life, and we don't have a lot of his writings. We have what his contemporaries reported about his argumentation. But he's credited with this idea that matter is made out of small particles that can't be divided into anything else. He called these small particles atoms, from the Greek word for indivisible. So you really need to know that Democritus is credited with this idea. But Aristotle's views dominated for a really long time, certainly in Europe. Now we're going to skip over large portions of history, talk very briefly about the alchemists, who were a very secretive group of researchers who developed a lot of practical knowledge. They had a lot of lab techniques and lab equipment. They discovered acids and can purify them. They weren't theoreticians. They were also really secretive, so it's hard to know what they were teaching. But in terms of progressing understanding of the nature of matter, they had a lot of skills, certainly. That's not really our focus either. So we're going to jump over more stuff. All right. If you are interested in alchemists, if you're interested in literature, go find the Canterbury Tale about the alchemist. It's fascinating. Chaucer did a wonderful job with that. Anyway, I digress. And let's go to Revolutionary era France with Antoine Lavoisier, the famous French chemist, who is often considered the father of modern chemistry. This is a famous portrait of Lavoisier with his wife Marie, who was brilliant in her own right, but we're focusing on Antoine for today. And among his many contributions to science, he identified oxygen and hydrogen as being elements. He had a very quantitative approach to his work. That he and Marie did a lot of their lab work together in their home laboratory, where he had thousands and thousands of pieces of lab equipment and commissioned some very, very precise balances, some of the best balances available in Europe at the time, because he was very wealthy. And so let's go talk about the experiments he did that helped promote an atomic theory. All right. And so some of the important experiments that he did involved the study of decomposition of mercury 2 oxide, which is a red solid. And I've got a picture of it here. He studied the decomposition of other metal oxides, which were referred to as calyxes. He did a lot of other experiments as well, looking at the masses of what you started with the reaction and how that compared afterwards, because there was a lot of debate about what was going on here. And what he found through his very, very careful and precise measurements is that the mass before the reaction equaled the mass after the reaction, not just for the decomposition of mercury 2 oxide into mercury and then oxygen gas, but for a lot of other reactions as well. So he very, very definitively showed that the mass is conserved. So this is called the law of conservation of mass. You need to know that it's credited to Lavoisier. Now, the diagram here is not Lavoisier's experiment, but it does sort of help drive that point home. The mass of the reactants equals the mass of the products. Matter is not gained or destroyed. It's conserved during a chemical change. All right. And this wasn't at all obvious until Lavoisier did such careful, detailed public experiments, in some cases with demonstrations, that everyone became convinced that matter was conserved during a chemical reaction. The next scientist I want to talk about is Joseph Proust, who was also a French scientist. And he was actually a contemporary of Lavoisier's. And Proust actually spent a lot of his professional career teaching in Spain. And he did a lot of really detailed work as well. But we want to focus on his major contribution here, which is the law of definite composition, sometimes called the law of definite proportions. Same thing. And what he found through his very careful studies is that if you have a pure sample of a compound, it's got the same ratio of elements on a mass basis, regardless of the source of the sample or the size of the sample. This was, again, a non-intuitive finding, because if your samples weren't pure or you didn't have really precise balances, you might not get evidence that's clear on this. But Proust was able to prove it very, very decisively. All right. So, for example, all right, if we want to look at some models of the law of definite composition, right? If we look at water and we break it down into its elements, 11% of the mass of a sample of water is always hydrogen, and 89% of it is oxygen. If we look at carbon dioxide and we break it down into its elements, 32% of it by mass is always carbon, and the other 58% is always oxygen. It doesn't matter where we got the samples or how we got the samples. Did we get the water because we took hydrogen gas and oxygen gas and reacted them? Did we get the water because we took tap water or ocean water and evaporated it and distilled it and purified it? The mass ratio is always the same. And that's a really important thing. So the law of definite composition is attributed to Proust. All right, so we've got some very important ideas here. Democritus and the idea of atoms, Lavoisier and conservation of mass, Proust and the law of definite composition. Right? They always have the same ratio of elements. So now we're ready to start thinking about the first atomic theory. And that was brought to us by John Dalton, the English scientist and teacher. He really thought of himself as a teacher. He started teaching at the age of 12 and spent a lot of his career in the classroom. He had a lot of different research interests, including meteorology and relative masses of elements, and of course, atomic theory and color blindness. And he really did a lot during his time. All right, he came from a very poor family of devout Quakers and really was devoted to his work. And in 1808, he published a book, A New System of Chemical Philosophy. And in that book, he proposed the first atomic theory, the first explanation of how matter works, putting all the pieces together, right? And so we're going to simplify it down to 5 statements, really, but we have to be able to incorporate Lavoisier's work and Proust's work in this theory. So, Dalton's atomic theory, the first statement, we can say that all matter is made up of indivisible particles called atoms. Now, of course, this goes back to Democritus, right? This is not an original idea of Dalton's, but he's putting it all together, and that's really important. Elements were already known by this time, a number of elements historically, and we know that, according to Dalton, atoms of each element are different from atoms of the other elements. So every element has its own kind of atom, is another way we could phrase this sentence. And all the atoms of an element are just like all the other atoms of that element in every possible way, said Dalton. Now, what Dalton couldn't tell us is what makes an atom of one element different from an atom of a different element. He couldn't talk about that. That's okay. It's the idea that we're really focusing on here. All right. Now, as I said, we need to be able to incorporate conservation of mass in definite proportion in the theory, or it's not a very useful theory, but Dalton did. And let's go on and talk about that on the next slide. All right. How did Dalton incorporate the law of definite proportions and conservation of mass? Dalton said, atoms of different elements combine in small whole number ratios to form compounds. So we're not destroying the atoms. We're putting them together in certain ratios. And if we look at them at an atom to atom ratio or an element to element ratio, we can now suddenly explain the law of definite proportions. All right. So if we think about water, all right, there are 2 hydrogen atoms for 1 oxygen atom. We know that that's the formula of water, right? And so we have a definite proportion of atoms on an atom level, and that explains the mass ratios. The hydrogen atoms have a certain mass, the oxygen atom has a certain mass. That's going to give us a consistent mass ratio for this compound. And we're putting them together and not destroying them, and so mass is conserved as well. Dalton actually went even further. Based on his own experimentation, proposed another law that's also considered to be part of his theory. And this is the law of multiple proportions. and this is, like I said, credited to Dalton. Atoms of different elements can combine in different whole number ratios to form different compounds with different properties from each other. As an example of the law of multiple proportions, we can talk about carbon monoxide, which is a colorless, odorless gas that's also deadly to humans. All right, but in carbon monoxide molecules, I have one carbon atom combined with one oxygen atom, so a 1-to-1 ratio. Now, this is a very different compound from carbon dioxide, which is also made from carbon and oxygen, but a different ratio. So I have one carbon atom to two oxygen atoms. All right, in carbon dioxide, we produce it in our respiration, and plants, of course, use it in photosynthesis to make sugars. Right, but very different properties for these two gases, although they're both colorless and odorless. Carbon monoxide is much more poisonous. So we've got this theory now, all right? Atoms combine in small number ratios. Matter's made up of atoms. Every element has its own kind of atom that's different from other kinds of atoms. So this is a really important step forward in terms of explaining matter. It's our first atomic theory. So just as a summary, our ideas about the nature of matter and the structure of matter have changed a lot as we've gotten more evidence. This continues to be the case, right? As we get more information, our ideas change. We change our theories. That's going to be an ongoing theme in this unit, certainly. So we need to know Democritus, the idea of atoms, Lavoisier, conservation of mass, Proust, constant composition, and then Dalton's statements, the first atomic theory. Some parts of Dalton's theory still hold. The idea that every element has its own kind of atom. The idea that atoms combine in small whole number ratios to make compounds, and they can combine in different ratios to make different compounds. The idea that every atom is exactly like every other atom, we now have evidence that shows that that's not quite the case, but that wasn't something Dalton was aware of. So it was a really good starting point and set the stage for the next 100 years of progress. We're going to end here. All right, I'll talk to you later.